So these are the instructions given in the book for how to predict molecular geometries. And most of them are great. Start out by drawing the Lewis structure. Figure out how many total number of electron groups. And from that, then you look at the number of bonding groups and the number of lone pairs. And this is so stupid. Refer to table 10.1. Well, that's great if you're doing homework. But on an exam, that's not going to work. Nope. I'm not going to give you the table. So that's bad advice. Think about how balloons would arrange themselves. So the number of electron groups is the number of balloons. And then imagine that however many lone pairs are the invisible balloons. Okay, so let's predict the molecular geometry and the bond angle for this guy, CLNO. Okay, so we're going to predict the geometry for this guy. First thing is Lewis structure. Triangle planar 120. Okay, that's your prediction. Oh, yeah, right past my head. There's a moth in the classroom. Step on it. That's not distracting at all. It's distracting me. Okay, Lewis structure. This is... And the class is just... I'm so glad the dean isn't here now. The chlorine has 7 valence electrons, and the nitrogen has 5, and the oxygen has 6, and I'm pretty sure that's 18. So we got 2, 4, 6, 8, 10, 12, 14, 16, 18. We're going to need a multiple bond, right? Because we don't have enough to give everybody an octet. So nitrogen has an octet, so let's take one of these lone pairs and move it to a double bond with the oxygen. Now we've got octets for everybody. And if we think about how many bonds do these atoms like? Chlorine likes 1 bond, nitrogen likes 3 bonds, oxygen likes 2 bonds. And so they all have the preferred number of bonds. They're going to have all 0 formal charges. So this is our Lewis structure. The central atom has how many groups? 3 electron groups. So 3 groups. How do 3 groups get away from each other? They make a triangle, right? Trigonal planar. So we could draw a picture of this. So 3 groups, right? So this is going to be my oxygen that's got a double bond, and then I've got these other 2 groups. But one of these groups is a lone pair. So that's a lone pair. It's there, but it's a lone pair. So we've got 1 lone pair. So we've got this left. What's the name of that shape? It's one of the really, really fancy not bent. Oh, man. This is bent. This is the molecular geometry. The electron geometry is trigonal planar, but one of those is a lone pair. So the molecular geometry is bent. It also asks us to predict the bond angle. If this was a perfect trigonal planar thing, what would the bond angle be? 120. Is it perfect? No. We've got this double bond and we've got a lone pair. These are both more repulsive. And so this is going to get closer together or further apart? Closer together, because this guy's repulsive and they're like, ew, I don't want to be next to you. Less than 120. That's good enough. Any questions?
So the molecular is when you forget about the lone pair?
Well, you don't. The molecular is not when you forget, but you make it invisible. Yeah, it's there, but you can't see it because it's still there, being repulsive. It's just invisible and repulsive. Okay, let's do I3 minus. Well, there's only one way to put 3 iodines together. You're just going to have to put them in a row, right? And then for electrons, 3 times 7 is 21. And then a negative charge means we have an extra one, so that's 22 electrons. So we got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. We need to stick 2 more electrons on here. We're going to put them on the central atom. We don't want to make a double bond because that's going to make things worse. You want to go to double bonds when you don't have enough. When you've got too many for octets, you definitely don't want to make more double bonds. So I'm going to scoot this guy over, and we're going to put the other lone pair on the central atom. Iodine is in period 4, 5. 3, 4, 5. Period 5. So it can do this. This is an expanded octet. So how many groups around the central atom? 5. So how do 5 balloons get away from each other? The little girl with the tutu, right? Trigonal bipyramid. That's the electron geometry. And the great thing about this is these will be, giving the names of these will be multiple choice, and so as long as you can pick the correct one out, you don't actually have to be perfect on your spelling or anything.
So let's say you had a lone pair and have like 2 points. So it's like a band molecular structure was tricovalent. What was it? Would that have resonance structure?
You can have resonance as long as you have some multiple bonds, double bonds or triple bonds.
So it wouldn't matter if it was just lone pair, it wouldn't change it.
The lone pair.
Because you could put it like anywhere, right?
So let's finish this one and then we'll talk about that one, okay? So this is the electron geometry, but it wants us to give the molecular geometry. So there are 3 lone pairs. These positions are not equivalent. This is a 90-degree angle, and these angles around the equator are 120. So we want to put the lone pairs where there's more space. So I'm going to put the lone pairs around the equator. Because there's more room. And then we describe the shape of just the atoms. What's that going to be? Linear. So linear is the molecular geometry. You have to look at the Lewis structure and the electron geometry before you can go to the molecular geometry. Okay? So, to your question about resonance, I think you were talking about maybe something like this, where we have a double bond and an atom there, and then a lone pair. Something like this, right? So if you have a double bond here, you could have resonance structures. So we could have the single bond there, and the double bond over here, and the lone pair. The geometry is going to be the same. Because whether the double bond is here or here doesn't affect the geometry. It's still going to be bent.
Really affect it in any way either.
Well, the lone pair does. If the lone pair wasn't here, this would be linear.
Well, besides the geometry, more like towards resonance.
The lone pair has no effect on resonance.
Okay.
No. This is an illustration from your textbook, kind of giving you an idea of how to represent these on paper. This part is very useful. The straight line means it's in the plane of the paper or the screen. A hatched wedge is like a dashed line. It's like behind the screen. And a solid wedge means it's coming out at you. Now, some of these are drawn that are fairly easy to see, and some of them are a little screwy. And it just takes a little bit of practice to be able to see these. But if you're taking OChem, this is, you got to learn how to visualize these things. Oh, this section goes on and on. Okay, larger molecules. Larger molecules are going to have more than one interior atom. And so what we do is we look at the geometry around each interior atom. So here's glycine. This is an amino acid. And this has 4 interior atoms. So we're going to look at the geometry around each one of them. For the nitrogen, we see there's 4 groups and 1 lone pair. So that's going to be a trigonal pyramid. This carbon has 4, stupid pointer, 4 groups, no lone pairs. So that's tetrahedral. This one has 3 groups, no lone pairs. That's trigonal planar. And here we have 4 groups, 2 lone pairs. That's bent. And so based on that, we can draw the structure. So here we have bent. This is flat. This is a tetrahedron, and this is a trigonal pyramid. Those are fun. So let's do this one real quick, and then we'll be done for today. So here we've got this molecule. These 3 hydrogens are bonded to the carbon, and then we've got carbon with a double bond to the oxygen, and then we have this oxygen. And so what I'm going to do is I am going to cheat a little bit and just amend this, turn it into a Lewis structure. So this had 3 hydrogens on it, and this has a hydrogen on it as well. And then if you go around and you take care of all the lone pairs, and, considering the total number of electrons, you're going to need some lone pairs over here and over here. So let's look at this carbon. How many groups? 4. Are there any lone pairs? No. So that one is tetrahedral. How about this carbon? How many groups? 3. Any lone pairs? On the carbon? Nope. So that is trigonal planar. And then the oxygen. How many groups? There's 2 lone pairs, a total of 4 groups, right? So 4 groups would be tetrahedral, but 2 of those are invisible, so what we have left is bent. Why is it 4? Because we have 2 bonds and we have 2 lone pairs. Lone pairs are groups. So a group is a single bond, a double bond is 1 group, a triple bond is 1 group, a lone pair is 1 group, and a single unpaired electron is 1 group. So this is the sort of thing that will probably be on the next exam. I'll give you something like this and ask you, what's the geometry around each of these? I will not ask you to draw it. But this question does ask us to make a sketch, and so I'm going to do that. So there's the, oh, that's too big. Here's the oxygen, and that's going to be bent. So I'm going to put, almost got him. Go out the door. Go out the door. Come on. Shoot, shoot. Got them off out the door. Okay. So this is going to be bent, and so the hydrogen is going to be there, and there's a carbon here. And then that carbon is trigonal, planar, so we have to try to get approximately 120-degree angles there with this carbon. And this one's tetrahedral. This is where things get a little tricky, because the rest of this is all flat. So we can have one of the hydrogens here, and one sticking out at us, and one going back. I don't expect you to become good at drawing pictures like that. I do expect you to be able to do this. Identify the geometry around each of the central atoms. Any questions? Pardon me?
The naming part.
The naming part. So this makes an excellent multiple choice test, because I can give you this structure and say, okay, what's the geometry around this carbon? And it'll be a bunch of geometries, you have to pick one.